Last class, we went over how to find the extreme values of a function that's continuous on a closed interval. So here I have the function f of x equals x squared, and I'd like to find the global maximum on the interval from -2 to +3. So the procedure was first find all of the critical values. So this is anywhere where the derivative is either 0 or it does not exist. And the derivative of this function is a simple one. F prime of x is equal to 2x. Okay, this derivative exists everywhere, so it's never going to not exist. But if you want to figure out where 2x is equal to 0, well, that's simply where x is equal to 0. So this is the only critical value of the function x squared. But of course, that makes sense. I mean, that's this spot right here where the derivative is equal to 0. Okay, if you want to find the global max and the global min on the interval from -2 to +3, all you really need is to look at a table of values. What you can do is check both of the endpoints, which is -2 and +3, but then also check every single critical value that falls within this interval. There's only one, and it does fall within the interval, and it's 0. Okay, so if you put -2 into the function, x squared is going to give you the value 4 back. That is right here. If you put 3 into the function, you get 9 back, and that is right here. And if you put in the critical value of 0, you get 0 back, and that's this spot here. So if you're looking for the extreme values, that is the global max and the global min of this function on a closed interval, you don't have to check every single point. You only have to check the endpoints and the critical point. Whichever one is the biggest is going to be the global max. That appears to be the 0.39. And the global min is going to be the 0.00. So this is the max, and this is the min. So I wanted to look at this really simple example just because it illustrates how the process works. If you have a more complicated function, the process is still the same. Perhaps just figuring out where the derivative is equal to 0 will take a little bit more work. All right, so that concludes what I wanted to say about extreme values of a function on a closed interval. What I'd like to talk about in the rest of this lesson is something called concavity. In the next 2 slides, we're going to define 2 terms. One is called concave up, and the other is going to be called concave down. And both these together we would call concavity. But it tells you the direction in which a function is bending. Like, is it opening upward versus opening downward? So let's describe this in the next slide. The concept of concavity is to describe a quality that a function has. You know, is the function bending or opening upward, or is it bending or opening downward? So to start with, let's look at something that is concave up, meaning that it is sort of bending upward. And here the function f of x equals x squared is concave up everywhere. It's always like bending and opening in this upward direction. I want to somehow connect derivatives to the idea of concavity, or in this case, concave up. So what I'm going to do is, again, we have the function f of x is equal to x squared. And I want to start by taking the derivative of this function. We did this in the previous slide, but the derivative is 2x. This derivative tells you the slope of this equation at every single point. In fact, you can graph the derivative itself. The derivative is the function 2x that is a line with slope 2 that goes through the origin. So it looks something like this. So here's the derivative. And the thing to note about the derivative in this example is that the derivative is increasing. It starts out negative over here, it becomes 0, and then your derivative it's positive, but it's increasing more and more and more. That tells you a lot about the slopes of these tangent lines. So by that I mean this. If you think about what the slope is equal to over here, well, it's some negative number. And as you move along the curve in this direction, the tangent lines, the slopes of them, are still negative, but they're less and less negative until they become 0. And over here, the slopes are becoming more and more positive. This correlates to a derivative that is increasing. So that being said, if the derivative is increasing, that means the original function is concave up. The fact that the slopes are becoming steeper as you move in this direction means your equation must be bending in this upward direction. So really, you can answer the question of concavity or concave up just by looking at your first derivative. The first derivative is always increasing, therefore the tangent lines are increasing themselves, and therefore your curve is opening or bending upward. But there's a better way that you can determine concavity, and it isn't by using the first derivative, but it's by using the second derivative. So what is the second derivative of the function f of x is equal to x squared? The first derivative was 2x, and the derivative of 2x is the second derivative, and that is just the number 2. Why is it useful to look at this thing? Well, the number 2 is always positive. So the second derivative is always positive. If your second derivative is always positive, that means your first derivative is always increasing. And if your first derivative is always increasing, that will force the original function to be concave up. So in some sense, it can be easier to look at the second derivative as opposed to the first derivative to determine concavity, because it's a simpler criterion. If you find a second derivative and you know that it's positive, that's the same thing as saying your original function is concave up, because that forces the derivative to increase, and that means the slopes of the tangent lines are increasing themselves. So this is an important connection. If a function is concave up, this is because the second derivative is positive. So what about a function that is concave down? How is that going to connect to the derivatives? So here I chose a function f of x equals negative x squared minus x plus 1. It is this thing here. Just by looking at its graph, I can see that it is concave down. It is bending or opening downward. So what is it about the derivatives that make this happen? If you start with the original function, which is negative x squared minus x plus 1, well, if you take the first derivative, it is negative 2x minus 1. And the thing to note about this function, the first derivative is decreasing. And I know this because it's a line with a negative slope. And you can also see it by graphing the function itself. I know it's equal to 0 at negative 1/2. It has a y-intercept of negative 1. Not a perfect sketch, but your function looks something like this. So this thing is the derivative. All right, so the derivative goes from positive to 0 to negative. That means you have very steep tangent lines that become more and more negative. That decreasing aspect of the first derivative causes your function to curve or bend in this sort of downward direction. It's like opening downward. So that comes directly from the fact that the first derivative is decreasing. But it may be easier in some cases to, instead of looking at the first derivative, look at the second derivative. What is the second derivative of this function? That is the derivative of the first derivative. And if I take the derivative of this function, I get the number negative 2. And negative 2 is always negative, or said another way, the second derivative is always negative. If your second derivative is negative, it must mean that the first derivative is decreasing, and that means the function is going to be concave down. So this is also going to be useful for us. If you want to find where something is concave down, check to see where the second derivative is less than 0. what we'll do next is look at functions that are both concave up and concave down and try to determine where that is actually happening. In example 2, what I'd like to do is figure out where this function is concave up and concave down. And I want to use derivatives to answer this question. So here I have a graph of the function. I mean, I don't know exactly where it's concave up and concave down, but this part of the graph appears to be concave down. But then starting somewhere around here, it appears to be concave up. I want to figure that out exactly, though. This is what that process will look like. Well, first of all, you need to know the second derivative, so therefore you have to have the first derivative. The first derivative is 18x squared plus 30x, and that's it. You could check to see where this thing is increasing and decreasing to get your answer. However, why don't we find the second derivative and then determine where that thing is positive and where it is negative. Okay, so the second derivative is 36x plus 30. Okay, so wherever this thing is a positive number, I know the original function is concave up. Wherever this thing is negative, it's going to be concave down. Instead of like focusing on where it's positive and where it's negative, I think it's a really good strategy to, figure out where is it equal to 0. It'll be really easy to solve this equation. If you know where something is 0, it must be either positive or negative everywhere else. And I think we can reason that out by using this graph. So where is 36x plus 30 equal to 0? Well, if I subtract 30 from both sides and divide both sides by 36 and simplify the fraction, I get that x is equal to negative 5 over 6. And, approximately, well, what is that? That's like 0.83, I think. So it's negative 0.83. Something like that. So that's a really close answer, but here it is exactly. All right, so on the number line, this is negative 1. So negative 5/6 is negative 0.83. I'm going to mark this spot right here. This is where the second derivative is 0. That means over here, it's either positive or negative, and over here, it's either positive or negative. Well, this thing's a line that's increasing, so I know the second derivative looks like this. Therefore, it's positive over here and negative over here. So I'm going to note that here. This is where the second derivative is 0. Over here it is positive. Over here it is negative. That's enough for me to say, oh, great. Negative second derivative, that means we are concave down. And where the second derivative is positive, well, that means we are concave up. Does that actually match up with what is happening on this picture? And it really does. So if you don't use this spot, but you're a little bit over here, the graph is concave down. So I'm going to highlight that. Let's see, it looks something like, this is where the graph is concave down until we get to right about there. And then, over here, the graph is concave up. And that connects to where the second derivative is either negative or positive. But there's something else that happens. What happens exactly at this spot where the second derivative is 0? At this one spot, which I'll mark on the graph, okay, this thing is not concave up nor concave down here. In fact, this is a spot on the graph where it changed from concave down to concave up. And that's what we're going to call an inflection point. So this thing here, inflection point, is this. An inflection point is a change in concavity. That's where a function either goes from concave down to concave up or concave up to concave down. So I'm going to make a note that if you have an inflection point, So, if there is an inflection point, then you know the second derivative is 0. This doesn't work the other way around. If your second derivative is 0, it isn't always the case that you have an inflection point. But I'll just note here for this problem that, okay, I first figured out where the second derivative was 0. I labeled it here, and it turned out that it was an inflection point because the concavity changed from concave down to concave up. And one more thing before moving on. When we're asking where something is concave down, I did actually highlight it on the graph, but you could also record your answer as an interval. The place where the graph is concave down is everything from -infinity up until we get to -5/6, not including that point. That is this part of the graph. Concave up is the interval that goes from -5/6 to +infinity. So technically you could record your answers like this, and that is everything for this problem. Let's build off of the ideas in the previous example to describe something that is called the second derivative test. So here in example 3, I want to use this second derivative test to find the local min and max values of this function. Really before we even do that, just to go over this again, a local min and max have to occur at critical values. Oh, and there are clearly two critical values just by looking at the picture of this function. This spot is a critical value, the derivative is 0 there. And this spot is a critical value, again, because the derivative is 0 there. But I'm noticing something that is different between these two critical points, and it has to do with concavity. So here we have a critical point, and the graph is concave up. So the points around it are moving upward. Well, if you have a critical point, and your graph is concave up, it must be that you have a local minimum value. If the curve is opening upward and the derivative is 0 here, it would have to be a local min. Likewise, over here, again, we have a critical point, and I'm noticing that the function is concave down. Well, if you have a critical point and your graph is bending downward, that must be that this is the highest value or a local max at this one spot. It's these ideas that are stated within the second derivative test. If you're looking for a local min, you find a critical point, and it must also be that the second derivative is positive. If your second derivative is positive, your graph is concave up, and your critical point must be a minimum. Likewise, if your second derivative is negative at a critical point, because the graph is bending downward, it has to be a local max. So let's use these ideas to find all the local min and max of this function. Again, we could use the graph, but I wanted to use this graph to illustrate how this test actually worked. If we're just using the function itself, for starters, you need the first derivative. The first derivative is -3x² plus 12. And you need critical points. So that means you have to figure out where this thing is either undefined or where it's equal to 0. Well, this thing exists everywhere, so the only thing I'm going to check is where is the first derivative equal to 0? I will subtract 12 from both sides of my equation. I will divide both sides by 3. And if I take the square root of both sides, I get two solutions, plus or minus 2. And that's exactly what this spot is here, and this spot is here. Now, again, we have the graph to look at to get our answers, but if we're just using derivatives, at this point, all we know is that we have two critical values, and technically without the graph, we don't know if they are local mins or maxes. But now you can use this test to actually determine what these are. But you first need to figure out what the second derivative is equal to. The second derivative is the derivative of your first derivative. That's very easy to compute here. It's going to be -6x. All right, so here's the second derivative. All right, so here we go. We're going to apply the second derivative test. Is x equals -2 a local max or a local min? What has to happen is if we look at the second derivative at this point, do we get a positive or negative number? If I put negative 2 into this function, you get negative 6 times negative 2, and that's positive 12. That means your second derivative is positive. You have a critical value that has a positive second derivative. That means your graph is concave up. That means you must have a local min. And this is what the second derivative test means. You're using the second derivative to test the nature of the critical points. Likewise, what about x is equal to positive 2? Is that a local max or a local min? What you do is you test it by putting that into the second derivative. When you do, you're putting positive 2 into the second derivative. Negative 6 times positive 2 is negative 12. That's a negative number. Okay, that means your function is concave down. But if you have a critical value and the graph is concave down, that must mean you have a local max. So here we go. We just included concavity to help us determine the nature of critical points. You can figure out if they're local mins or maxes just by using the second derivative. All right, so let's try this again. So I want to use the second derivative test to find the local min and max of this function. All right, so I'm not looking at the graph yet, so I'm going to go directly to taking derivatives. And for starters, I need to know what the critical points of this function are. So I need the first derivative. All right, we have a product, so I have to use the product rule. We get 2x times e to the x plus x squared times e to the x. All right, so if I want the critical values, that's wherever this thing is either undefined or equal to 0. It's always defined, so I'm just going to check to see, well, where is 2x e to the x plus x squared e to the x? Where is this equal to 0? I think it'll be helpful to factor this equation. That way we can check to see where each factor is equal to 0. In terms of factoring out a greatest common factor, there is an x and an e to the x that's common to both terms. If I factor out an x and an e to the x, I'm left with just this 2. And if I factor out one x and this e to the x, I'm left with just an x. I can now check to see where each of these three things are equal to 0. So I'm going to set, well, x, where's that, equal to 0? I mean, that means x equals 0 is actually a critical point. Great. Where is e to the x equal to 0? I have to check that too. And the answer is nowhere. The function e to the x is an exponential function. It's always positive. It's never 0. That won't include any critical points. But where is 2 plus x equal to 0? That would be x equals negative 2. So there are two critical points, x equals 0 and x equals negative 2. Are they local max or min values? I don't know, but I'm going to try to use the second derivative to determine this. All right, so we got to find the second derivative. That means we're taking the derivative of this thing. I think this will take a little bit of work. Yeah, but let's do it. So the second derivative. I want to make sure I have enough room here, so I'll put, all right, we're finding the second derivative of this function. So I'm taking the derivative of this thing. So I'll start here. The derivative of 2x is just 2, then times e to the x. I add on the 2x times the derivative of e to the x, which is just e to the x. And then I add on the derivative of x squared e to the x. Oh, well, the derivative of x squared e to the x is actually this entire thing again. So I'm just going to copy this whole thing down. So that is, we get 2x e to the x plus x squared e to the x. Okay, here it is. That's the second derivative. I think we can maybe combine some terms, maybe factor it a little bit. We have 2e to the x. We have 4x e to the x, and then x squared e to the x. I mean, really, we don't have to, I think, take this any further. We just have to plug numbers into the expression, but just to be careful, I think I'm going to factor out an e to the x from every single term. I'm left with 2 plus 4x plus x squared. Okay, I'll leave it like that. This is my second derivative. Okay, great. Is this critical point a local max or local min? I'm going to put this number into the second derivative to see if it's positive or negative, and we'll go from there. All right, here we go. Second derivative at 0 is equal to e to the 0 times, all that stuff's just going to be 2, right? That's going to be 0, that's going to be 0. So e to the 0 is 1, and 1 times 2 is 2, and that's positive. What does this mean? This means the graph is concave up, therefore we have a local min. All right, what about -2? Let's try that one. Okay, if I put that into the function, I get e to the -2. Then I get 2 minus 8 plus 4. And is this thing positive or negative? This is f double prime -2. That is e to the -2 multiplied by -8 plus 6 is -2. E to the -2 is positive. I don't really even care what the number is. I know altogether it's going to be a negative number, and that means that this thing is a local max. So without even using the graph, I know this to be true. If I look at the graph of this function, at x equals 0, there's going to be a local minimum. At x is equal to -2, I'm expecting to see a local max. There's a graph of this thing on the next slide. Let's check it out. And that looks correct. Here, at -2, that is definitely a local max. The function is concave down, and we have a critical point, so it's a max value. Here at 0, that is definitely a local min. Again, that was because the graph was concave up, and we had a critical value at this spot.